We now want to look at some differential equations that require substitutions in order for them to work. And so these are going to have two different names each as we go through them. So the first one we're going to talk about is a Bernoulli differential equation. But you can think of a Bernoulli differential equation as almost linear, because that's really what's going to happen. In a Bernoulli differential equation, we're going to do a substitution and it'll become linear. So let's think about what a linear differential equation looked like. A linear differential equation was dy over dx plus p of x times y equals q of x. To make it a Bernoulli, we're simply going to have a y to the n at the end. So we have that extra piece there on the far right term. So to solve this, well, I want to make it linear, so the first thing I'm going to do is do a substitution. I'm going to let v equal y to the 1 minus n. Now what I'd like to do is come back to my differential equation above and get rid of the y's and make it linear with v and x. Well, I have v, so let's find dv dx. Because I have dy dx, so let's find dv dx. So I'm going to take the derivative with respect to x. Y is a function of x, so I'll do the derivative of y. And if I do 1 minus n minus 1, I just get the negative n power. But then since y is a function of x, I have times dy dx. And I'm eventually going to need to solve for dy dx, so let's go ahead and do that. So dy dx would equal 1 over 1 minus n. 1 over y to the negative n is just y to the n, and then dv dx. Now what I would like to do is actually plug that into my differential equation. So instead of dy dx, I'm going to have 1 over 1 minus n, y to the n, dv over dx, plus p of x times y equals q of x times y to the n. Now I have y's, v's, and x's. This is just all sorts of a mess. So let's multiply by 1 minus n on every term, and let's divide by y to the n on every term. So doing that, I have dv over dx. Now, let's go back. What happens? So I need to multiply by 1 minus n, and then divide by y to the n. So I'd have 1 minus n times p of x times y to the 1 minus n. And then on the other side, I'm going to have q of x times 1 minus n. And if I divide by y to the n, that's all I have. Well, this is better. I only have one single y, but remember our substitution. Our substitution was v was y to the 1 minus n. I'm going to rewrite that other side. This is now linear with v as the dependent variable and x as the independent variable. This that I'm boxing in red is my new p of x, and everything on the right that I'm boxing in blue is my new q of x. Now I can solve it as a linear. But be careful when you solve it as a linear, because you're going to have v equals when I solve it. Now, the key thing you need to know when you're solving a Bernoulli differential equation is not to go through these 5 steps. Step 1 is the big step. Let v equal y to the 1 minus n. But then you can skip all the way down to step 5. And as we do examples, that's exactly what I'm going to do. So let's try an example. So let's look at dy over dx minus y equals e to the 2x y cubed. And this one's nice. It's already in our linear form. So p of x is -1, and q of x is y cubed. Oops, sorry, not q of x. I do want q of x, but q of x is e to the 2x. N is 3, because I have y cubed. All right, now how do I solve this? Well, I'm going to let v equal y to the 1 minus n, but 1 minus 3 is -2. Now I'm going to skip to step 5. Step 5 was to write dv over dx plus 1 minus n, which is -2, times p of x times v equals q of x times 1 minus n. I keep forgetting to do that first, so times -2. Let's clean this up. dv over dx plus 2v equals -2 e to the 2x. This is now linear. So to solve it, I need to find my integrating factor. So that's e to the integral of my new p of x. Well, my new p of x is what's in front of v, which in this case is just 2. So my mu is e to the 2x. Then for linear, I have y equals, but that will be v equals here. V equals 1 over mu, so 1 over e to the 2x, times the integral of mu times q. And I'm going to write that as e to the -2x times, well, I have the integral of e to the 4x, and that's 1/4 e to the 4x plus c. When I was solving linear differential equations, I could stop here. I'm going to go ahead and rewrite it. So I have v equals e to the -2x times 1/4 e to the 4x plus c. When I was doing linear differential equations, I could stop because I've solved for my independent variable. But my independent variable in the original problem was y, not v. So I've got to get back to y's. Well, I know v is y to the -2. So that's y to the -2 equals, and I'm going to go ahead and multiply this out. 1/4 e to the 2x plus c e to the -2x. Remember, my goal is to solve for my dependent variable if possible. For linear, it's always possible. Same with Bernoulli. So I'd have y equals 1/4 e to the 2x plus c e to the -2x, all of that to the -1/2 power. And there's a Bernoulli. So with a Bernoulli, to recap, do your substitution. So your v equals y to the 1 minus n. Go to your new linear differential equation, and then solve it as a linear. When you solve it as a linear, though, you should get an answer in terms of v first. You will then need to plug in your substitution to solve for y, your original dependent variable. So Bernoulli differential equations technically are also almost linear, but typically we'll refer to them as Bernoulli, but it might help to think of them as almost linear. The last differential equation we want to talk about for solving first order is a homogeneous differential equation. Sorry, I was moving my notes. So a homogeneous differential equation, but just like the previous one, this is going to be almost separable. So that means we're going to do a substitution, and it becomes separable. So remember, separable differential equations were dy over dx equals some function of x and y, which I could write as q of x or g of x times h of y or p of y or whatever letter you want to use. To be homogeneous, though, I need to be able to write this as a function of y over x. That's the catch. So homogeneous differential equations are going to be a little bit tricky. I have to be able to get my differential equation into a function of y over x. That can sometimes be messy. We'll talk about that as we do examples. If I can get there, Now to solve, well, I need a substitution. So I'm going to let v equal that y over x, or y equals v times x. Taking the derivative, dy over dx now equals, well, v is a function of x, so I've got a product rule. So derivative of the first with respect to x times the second left alone, plus the first times the derivative of the second. So dy over dx equals dv over dx times x plus v. If I plug that in now, I have dv over dx times x plus v equals some function of v, because y over x is v. I can now separate this. Okay. So dv over dx times x can equal g of v minus v, and then I'll have to divide and multiply the x. At this point, it's hard to see that it actually is, that it's going to be nice. Hopefully you can see that it's separable. I'm going to have dx over x on the right-hand side, and then dv over g of v minus v. But depending on what g of v is, this could be very nasty on the left-hand side. I may have to do a lot of simplification. And we'll see that as we do an example. So let's take a differential equation. 3x squared minus y squared dx plus xy minus x cubed y to the negative 1 dy equals 0. All right, if you saw this on your homework or a test, you might try to see if it was exact or almost exact. Now, it might be exact or almost exact. I don't want to do that though. After I solve it as a homogeneous, we'll see if it's the others. But I'm going to tell you that this is homogeneous, and let's see what we need to do. So what I really need to do is get dy over dx by itself. So I need to move 1 over and then divide. So I'm going to go ahead and jump to what dy over dx is. If you need to do that in multiple steps, go ahead and do that. And as I do that, I'm going to flip the order on the dx term so that I don't have to worry about that negative. So I have dy over dx equals y squared minus 3x squared, that had to flip because of the negative by moving it over, divided by xy minus x cubed y to the negative 1. That y to the negative 1 there is a very big problem. So let's suppose I wrote it as x cubed over y, and then I'd like to get rid of that fraction. So I'm going to multiply everything through by y. So I have y cubed minus 3x squared y over xy squared minus x cubed. Notice the power on every term is cubed now. Previously it was squared, but now everything has positive powers and it's cubed. That's going to be very helpful. I'm looking for those pieces, if I have something like this, to have the same power so that I can try to get y over x everywhere. All right, I need y over x everywhere. Well, since everything is cubed, now I'm going to do a weird thing of dividing everything through by x cubed. So I have dy over dx equals y cubed over x cubed minus 3y over x all over y squared over x squared minus 1. And hopefully you can see that that is a function of y over x. Every variable term has y over x. I do have some constants, but that's okay. So now I'm going to let v equal y over x. Well, when I do that, I know that dy over dx equals always dv over dx times x plus v. So let's plug all that in. So I'd have dv over dx times x plus v equals, well, let's change everything to v on the right-hand side. V cubed minus 3v all over v squared minus 1. Now, I'd like to subtract v from both sides, but on the right-hand side, I really need to have that common denominator, so I'm really going to subtract v cubed minus v. So that when I do that, I get dv over dx. We're going to go from page to page. So dv over dx times x equals, I have v cubed minus v cubed, so those cancel. And then I have negative 3v plus v, so I'd have negative 2v all over v squared minus 1. This is supposed to be separable. So I need to move the v's to the left-hand side because the dv must be in the numerator. So I'd have v squared minus 1 over negative 2v dv equals dx over x. And they must be that way. The dv and dx must be in the numerator. Now I need to integrate both sides. Well, the right-hand side's pretty easy. Right-hand side is just 1 over x. I know what that is. Left-hand side is a little trickier, but it's not that horrible. In this case, I can just split the fraction. So I'm going to make it the integral of negative 1/2 v plus 1 over 2v dv. I'm going to leave that side alone. Well, the integral of negative 1/2 v is negative 1/2 v squared, and I forgot to divide by 2, so negative 1/4 v squared, plus 1/2 natural log of v, put that in absolute value, equals natural log of x plus c. All right, not bad. I've solved this. Now in this case, I couldn't solve for v if I wanted to, but I cannot leave my answer here. My original variables were y and x, so I must get back to y and x. But what was v? V was y over x, so I'll have negative 1/4 y over x quantity squared plus 1/2 natural log of the absolute value of y over x equals the natural log of the absolute value of x plus c. Now you could do a little simplification. Natural log of y over x is just natural log of y minus natural log of x. There's a little bit of simplification you could do, but unfortunately I can't simplify it any further. I'm not going to be able to solve for y, and so I'd actually leave my answer there. There's a homogeneous differential equation. But let's go back to our example. I said when we started that it was in the form of an exact differential equation, but I also knew it was homogeneous and I wanted you to solve that. So let's see if this happens to be exact. So the partial of m with respect to y is negative 2y. The partial of n with respect to x is y minus 3x squared y to the negative 1. Well, those aren't equal, so it's not exact. Let's see, though, if we can get it to be a form of x or y. This is also good practice, just to see if you can remember those previous methods. So remember, for x, I take the partial of m minus the partial of n all over n. And for y, I take the partial of n minus the partial of m all over m. All right, need to do a little simplification. So I'm going to do the same trick. I'd like to get rid of the y to the negative 1. So I'm going to combine the first two, but I'm also going to multiply everything through by y. So I have negative 3y squared plus 3x squared all over xy squared. Oops, that's a minus. Minus x cubed. Well, let's see. I can factor out an x in the denominator. I can factor out a negative 3 in the numerator. Oh, and I get negative 3 over x. So this is exact. I got lucky that the first one I tried actually worked. So this has an integrating factor of x. And now I could solve it. Now I could try to see if it worked for y. The problem in y, though, is I am going to have 3y minus 3x squared y to the negative 1. So that looks promising. I have 3x squared minus y squared. If I multiplied through everything by y, I'm going to have a 3y squared minus 3x squared in the numerator. That looks pretty good. I could pull out a 3. In the denominator, I have to also multiply it by y. So I could factor the y out of the denominator, the 3 out of the numerator, but I don't have a 3 in the denominator to factor out, so I can't get that function of y, which is good because I should have a function of x or a function of y, not both. So this is actually also almost exact. So let's see if we can find our integrating factor. So mu of x would be e to the integral of negative 3 over x dx, which would give me x to the negative third. Oh, okay. I could now solve this as an almost exact. When I solve this as an almost exact differential equation, though, I'm probably going to get a very, very different form than what I had when I solved it as a homogeneous. What I would hope, though, is that basically if I moved the negative natural log of x over, I would have equivalent solutions. So let's actually try that. Let's see if we get the same solution. So I went ahead and multiplied through. I'm going to go back. I multiplied everything through by x to the negative third. So I get 3x to the negative 1 minus x to the negative third y squared dx plus x to the negative 2y minus y to the negative 1 dy equals 0. Let's check those partials. So the partial of m with respect to y would be negative 2x to the negative 3y. Partial of n with respect to x is negative 2x to the negative third y. Those are, in fact, equal. So now I can solve. So that was really step 1. Kind of. Step 2, f of xy would equal the integral of one of them. Let's just do m since it's first. You could do n. There's nothing special about which one you pick. So the integral of 3x to the negative 1 is 3 natural log of the absolute value of x plus, well, it'll be x to the negative 2 y squared. So divide by the power. So I'm going to have 1/2 x to the negative 2 y squared plus g of y. Taking the partial with respect to y, I get x to the negative 2y plus g prime of y equals n, which is x to the negative 2y minus y to the negative 1. So g prime of y is negative y to the negative 1. So g of y is negative natural log of the absolute value of y. So I have, for step 4, f of xy equals 3 natural log of the absolute value of x plus 1/2, I'm going to write it as y squared over x squared, minus the natural log of the absolute value of y, and that equals c. Now, this is supposed to equal my answer here, which is negative 1/4 y over x squared plus 1/2 natural log of y over x equals natural log of the absolute value of x plus c. So I'm going to rewrite both of those to a new page. So in just a minute, you're going to see both of that. All right, so I rewrote my two solutions. I'd like to show that these are equivalent. So I'm going to take our homogeneous solution because I think that may be one of the easier ones to work with. The first thing I'm going to do is multiply everything through by negative 2. If I multiply everything through by negative 2, I get 1/2 y over x squared minus natural log of y over x equals negative 2 natural log of the absolute value of x plus c1. Okay, so let's see. So I have 1/2 y over x squared. Let's separate this middle term. Minus the natural log of the absolute value of y plus the natural log of the absolute value of x. And if I bring the other natural log of the absolute value of x over, well, I have the 1/2 y over x. I have the minus natural log of y. And when I combine these, I have the 3 natural log of x. My two methods gave us the same solution. They don't look the same if I left them in their corresponding pieces up here, but they are equivalent. So that's kind of nice. It's nice that if I solve it 2 different ways, I get the same answer. Now in this case, like I said, solving both the homogeneous and the almost exact, I would not solve for my dependent variable, so it might be hard to see at a quick glance that they're equivalent, but as you can see from the algebra here, they are in fact equivalent. And so there's solving first order homogeneous and first order Bernoulli differential equations.